Okay, just to remind you where we are, this is Lecture 9, Atoms and Spectra. This is the course schedule, and what I've circled there is the first part of the course, which is kind of the intro, where we're talking about the basics of gravity and of atoms and of electromagnetism. And today is the last lecture of that intro section. Then we have the course is called Stars and Galaxies. It should really be called Introduction, Stars, Galaxies. The second section of this course is all about stars. We start with the sun and then talk about how stars evolve, how they die, and then we talk about the fun stuff like black holes. The last part of the course is about galaxies and the universe. In particular, we talk about life in the universe, the beginnings of the universe, and the end of the universe. The end of everything. And then we're done with we finished with two sections. One is the class presentations that you all are responsible for. We talked about that earlier. I would like to get your all topics by the end of this month. We'll talk a little bit more about that later. And then, of course, we have the final exam. So what we're going to talk about today is what can we know by just looking at a star? Looking at with our eyes or looking at with telescopes and with various instruments that detect the electromagnetic radiation. Well, if we don't know the distance of the star, we can still know a lot. And I'm going to tell you a bunch of things we can tell by looking at the star. And then today's lecture is how we can know that. So certainly without the distance of the star, we know its brightness. Duh. We know its color. It's easy. We know its temperature. And today's lecture will be how we know its temperature just by looking at it. And frankly, just by looking at the color. I can look up, see a star, and I can tell you instantly, within a reasonable uncertainty, how hot or cold it is. What its composition is. How on earth can we do that with something? There was a famous scientist in the 1840s who said, there is nothing more certain in this universe than the fact that we will never know what the heavenly bodies are composed of. Just 5 years later, he was spectacularly proven wrong. Okay, we know exactly what the heavenly bodies are made of, out to the 70 billion light years away. We know how fast it's approaching or speeding away from us. And we know whether or not it's got exoplanets. We know all of that without knowing its distance. We also know its magnetic field and how active it is. Our star, our sun, is not terribly active compared to other stars, and which is really good news, because if it was active, we would be dead. We would not be here. The surface would periodically be sterilized. Now, if we are able to calculate the distance to the star, then we will know its luminosity, how bright it really is. We can know its absolute size. We will be able to tell you how old it is, which is kind of miraculous. What its past history is and what its future history is. So just by looking at it and knowing its history, I can know what its entire past was and what its entire future is. Imagine if that was true with human society. You look at someone walking down the street and you can tell them everything there is to know about how they were born, how they grew up, what their family life was like, and you know exactly what their future holds. Actually, it's a good thing that isn't true. You can tell a lot about its friends and family, the stars that are around it. So today's lecture is where we go over how we can know all of this just by looking at it, okay? And to do that, we need some equations. And here are the equations. We'll be going over this one by one. Now, you notice we've actually covered almost all of these equations that are on the main formula sheet. So the intro part of the course is very equation heavy, and it's just the latter part of the course where we really don't use that many. We use the fruits of that labor, but we don't introduce that many new equations. These are the equations we'll be covering today. Okay. And again, the electromagnetic spectrum, going from the highest energy gamma rays to the lowest energies, radio waves or gamma rays, X-rays, ultraviolet, visible light, infrared, microwave, and radio waves. And it's through this electromagnetic spectrum that we know the universe. And in particular, this is an equation you really need to know, not only for this course, but for your life, because people will ask you this at parties, you know, what's the relationship between wavelength and frequency for light? I mean, this comes up all the time in casual conversation. Wavelength times frequency equals the speed of light. All electromagnetic radiation travels at the speed of light. It's kind of a misnomer why they call it speed of light when it's really the speed of radio waves, the speed of gamma rays, the speed of X-rays. And the energy of that light is inversely proportional to the wavelength, directly proportional to frequency. So higher frequency means a higher energy, lower frequency means lower energy, longer wavelength means lower energy. Okay. So this is why high energy, such as gamma rays and X-rays, is something you really need to watch out for. That's why your dentist will walk out of the room anytime you get a dental X-ray, because those X-rays are dangerous because they're extremely high energy and they can damage cells in the body. Okay. So today we're talking about 4 subjects. We'll be talking about atoms. Just this should obviously be an introduction for all, a refresher for all of you. We'll talk about electromagnetic absorption and emission in those atoms. Then we'll talk about black-body thermal radiation. For the purposes of the course, black-body radiation and thermal radiation are one and the same. We'll also use the term continuous radiation, and it's unfortunate that astronomers use those 3 terms for the same concept. So black-body, thermal, and continuous radiation all refer to the same topic. And then we'll cover the Doppler effect. Okay. So here's atoms and molecules. This is a molecule. Molecules made up of atoms. Molecules don't really show up too much in this course. A little bit when we talk about a gas between stars. But mostly today we're going to be talking about atoms. Everything in the universe, well, everything in our normal universe is made up of atoms, the matter that is. An atom consists of a proton and a neutron. Proton and a neutron are the heavy particles that are at the center of the atom. A proton has a positive electric charge of 1, a neutron has a charge of 0. Again, this is review for all of you. You had to have had this before you, got accepted to NC State. The electron is the light negatively charged particle that swirls around it. Every textbook in the world shows it like this. That's not the way it really is, but that's the way we designate that. And there's something that is not quite right here, and that's that the protons and the neutrons, if this was to scale, it would be the size of a grain of sand compared to the house. So the grain of sand would be the neutrons and protons, and the house would be where the electrons are. So atoms are mostly empty space, but they consist of a positively charged nucleus, which consists of protons and neutrons, and negatively charged electrons, which are in a cloud. And most of the material that we interact with day to day, the number of neutrons and the number of protons match exactly, so it's electrically neutral. There's no electric charge and no electric force with these particles. The number of protons determines the element. That would be hydrogen, helium, oxygen, iron, silicon. Everything, every part of normal matter is an element counting the number of protons that are in the nucleus, okay? The number of electrons determines the ion. So if the number of protons and electrons match, it's an atom. If the number of protons and electrons do not match, well, that object is now positively or negatively charged, and we call that object an ion, okay? And we don't talk a lot about this in the course, but the number of neutrons can vary. It's usually approximately the number of protons. So helium has two protons and 2 neutrons, but there's something called helium-3, which is 2 protons and 1 neutron. And I don't know if there's a helium-5, but there could be. So if the number of neutrons vary, those variations in the neutrons are called isotopes. And here's the thing, not so much for this course, but just for your general knowledge. Isotopes act exactly the same. So all carbon atoms act exactly the same, regardless of how many neutrons there are, and regardless of what isotope it is. There's carbon 12, carbon 13, carbon 14. And they all act exactly the same. Your body is made up of some of each of those isotopes, and you have no way of knowing the difference. So an element is the number of protons. An ion is any time that protons and electrons do not match up, and an isotope is where you vary the number of neutrons. Okay. How can you tell how many neutrons an element has? You can look it up. It's on the periodic table. There's no equation for it because it requires extremely complex quantum mechanical calculations.
The rest of them is more than one.
I'm sorry? And so every, most of the heavy elements will have multiple isotopes, but which of those isotopes are stable requires very complex calculations, way beyond this course, and actually way beyond anything I was taught. That's the realm of nuclear physics. What is empty space? A vacuum. We're going to be getting into that in the third part of the course. Are we going to need to know the difference between the atom models? You are definitely going to know elements, ions, and isotopes. Absolutely, not only for this course, but for your life. One of the greatest breakthroughs in all of science was what was called the atomic theory, which was developed in the latter part of the 19th century, early part of the 20th century. And it was Albert Einstein who actually conclusively proved that atoms exist. Everything is made of atoms, and all atoms of the same element are exactly the same. Those are the two most profound statements of all of science. And yes, you will need to know that. Is the PowerPoint posted on the website? It's posted immediately after this lecture. Well, actually, it takes me 20 minutes to convert it, but yes, they are. All of my presentations will be posted on website. Although I would, you should listen to me because I'm much more entertaining than watching a dead PowerPoint. Okay, so if there's an electron missing, which the electron just went away, that's an ion. If the proton goes away, it's now a different element. We're no longer carbon, we're nitrogen, for example. And if the neutron goes away, then it's just a different isotope. Okay.
Hi, I'm Emerald Robinson. In this What Is video, we're going to take a closer look at atoms. All matter is made of elements, substances that cannot be broken down by chemical activity. An atom is the smallest particle of an element that retains the element's properties. Atoms are the building blocks for everything in the universe, including ourselves. People often think of atoms as the smallest possible forms of matter, but even smaller particles make up atoms. Each atom has a dense center called a nucleus. The nucleus contains neutrons, which have a neutral electric charge, and protons, which are positively charged. The number of protons in an atom determines an element's physical properties. No two elements have the same number of protons. Revolving around the nucleus like planets around the sun are negatively charged particles called electrons. Electrons and protons attract each other, so atoms usually have equal numbers of the two particles. Scientists assign atoms an atomic number and atomic mass unit. The atomic number is the number of protons present in the atom. For instance, a helium atom has 2 protons, so helium's atomic number is 2. Add the number of protons and neutrons in an atom's nucleus together, and you get the atomic mass unit, or AMU. A helium atom has 2 protons and 2 neutrons, so has a mass of 4 AMU. Electrons have almost no mass and are not included in AMU calculations. While an atom's number of protons remains constant, individual atoms can lose or gain electrons. Atoms with different ratios of electrons to protons are called ions. Atoms of the same element can also have extra neutrons. Scientists call atoms with extra neutrons isotopes. Despite having different neutron counts, isotopes retain their elements' chemical properties because the number of protons remains constant.
For thousands of how-to and advice videos on any topic, visit monkeysea.com.
I have a question here. How do you tell how many neutrons are in an element? I don't want to be flippant here, but you weigh it. There's many ways to weigh it. You can calculate using Avogadro's number and thermodynamics, but you just weigh how heavy it is. And so, for example, 1 mole, one group of carbon-12 atoms weighs less than 1 mole of carbon-13 elements. And in fact, it weighs 1/13 less. Okay. So you just weigh it. Now, to weigh it, you got to know the number of atoms, and that requires thermodynamics. But that's basically the way you do it. And in fact, that's the way you separate isotopes, because isotopes all work the same chemically. If you spin them in a centrifuge, then the different weights of those isotopes will fall in different parts of the centrifuge. And this is, in fact, how you make enriched uranium to make nuclear power plants and nuclear bombs. Okay. Now we're going to talk about absorption and emission. Why did we talk about atoms? We talked about atoms because everything in the universe is made of atoms. Atoms tells us what it's made of. And knowing that we are made up of oxygen and carbon and hydrogen and helium and nitrogen and phosphorus is interesting, and really tells us how we function. So it would be really nice to know what atoms make up the cosmos, what atoms make up a star. And we do that with the process called absorption and emission. So here is this schematic of an atom. You got the nucleus marked by a P for just the proton at the center. Then you have the electrons. In electrons, instead of in one location, we now have multiple positions for the electrons. And the reason why is the electrons can have different, what we call energy levels around an atom. That electrons can be very close to the nucleus. If they gain energy, they will go to a different orbit. And quantum mechanics tells us that the electrons cannot be in any place around the nucleus. They can only be in certain fixed places. This is the genesis of the word quantum, that the electron has to be here, or it has to be there, or it has to be there. And to go from here to here, it's like a spaceship. To go to a higher orbit, it requires the addition of energy. These are called in states. So n equals 1, 2, 3, 4, 5 for the quantum mechanical levels. Unfortunately, quantum mechanics is beyond this course, but just take my word for it. And you have seen this in your high school physics or chemistry. Actually, you should have seen it in both. So if the electron wants to go from the n equals 1 level to the n equals 2 level, you have to add energy. If the electron goes from the n equals 2 level down to the n equals 1 level, you lose energy. And the way you gain or lose that energy is through electromagnetic radiation. So what it does is, if an electron absorbs what we call a photon, a bundle of electromagnetic radiation, and again in this course, photon and electromagnetic radiation, we're going to use those as synonyms, although they aren't really. The electromagnetic radiation comes up and bumps it up. But because these levels are in exactly the same position, they cannot vary, this light beam that comes up and it's absorbed, it has to be of a very specific energy. It can't be a little greater or a little less, because if it is, that electron cannot go to that level. So in fact, what happens is, if you shine light, this is a rainbow, and if you shine light that consists of a whole series of frequencies of electromagnetic radiation, invisible light, we call that a rainbow, okay? So blue is very high frequency, high energy light. Red is low frequency, low energy light. And when you look up in the daytime, the sun is producing light of all of these different wavelengths. We know this because when you see a rainbow, this is exactly what you see, or you see a prism. The the rainbow or the prism will break the light into its component frequencies, and we see those component frequencies as different colors. And here, notice there's this dark line. There's this dark line because that photon has come in and the electron has absorbed it, but only of that particular energy. Electromagnetic radiation of this energy or that energy, it will not be absorbed because there's no level that corresponds to that energy. So this is electron absorption. So when you see an electromagnetic spectrum that has a dark line into it, you can say, aha, this particular element has absorbed that particular frequency of light. And here's the thing, here's the kicker that was discovered in the 1840s that made all the difference, that made it possible for us to discover what the cosmos is made of. That particular light is specific to particular elements. It's like a barcode for the universe. So when I see that particular frequency, I know, aha, this is helium or this is hydrogen, okay? So we have another frequency of light. This is a lower frequency, and it goes up between the levels. And notice there's less difference between the n equals 2 to n equals 3 level. And so there, it's absorbing energy of a lower frequency, and you can see it's over here. It's much more towards the red. So those are two examples of photon absorption producing dark lines in a spectrum, and I can say there are these atoms that are between me and the light source that are absorbing these particular photons, and the exact energy of these lines tells me exactly what the element is. Okay. Now we talk about emission. So this was where the electron absorbs an electromagnetic radiation. What happens if the electron is tired being up at n equals 3 and it wants to come down? Well, then when it comes down, it has to get rid of that energy, and it gets rid of that energy by emitting a photon, okay, by emission, okay? And again, if it drops a big level, then the amount of energy is going to be higher, as you can see by the dark line. So absorption is dark lines on a continuous spectrum. Emission are these bright line features where we're seeing the photons escape from the electromagnetic, from the atom, okay? So, and here's the thing. Here's the hydrogen absorption spectrum, and here's the hydrogen emission spectrum. The frequencies match up exactly because the levels, the energy levels of particular elements are exactly the same, okay? So this is where we see an electron, a bunch of atoms where the electrons are what we call excited. They're at these higher levels, and when they drop down, they will emit these lines. And here we have a bunch of atoms where the electrons are all at a low level, and they absorb electrons and they go up, okay? How come we don't see green hot fire? Joseph, I will talk to you about that in about 20 minutes. That's a good question. So let me go to a demonstration here. Okay. Okay, so here is an atom. I'm sorry, it's a schematic of an atom. Instead of round, it's just flat. Here's a bunch of electrons that are in the lowest energy state. And when I click, the atom, the electron has been excited, and it's gone from the ground state n equals 1, n equals 2, n equals 3. It's gone up 2 levels. And when it did so, and so what's happening is somehow these electrons are being excited. They're being put in higher levels. And when this electron dropped all the way down to the lowest level, it produced a blue photon, blue light, which is very high energy, okay? And again, we continue to excite the electrons. And here one drop down just from this level and produce light that isn't quite as high energy. Another one. And here we drop not all the way down, but just between these two levels, and we produce a relatively low energy light. And as we continue to excite the electrons, put them in the higher levels, and those electrons drop down, what happens is we've got this emission spectra. And that emission spectra will match exactly with the energy levels between this. So Cole, you're responding to Joseph's question about how come we don't see a green out fire. Yes, we'll be covering black body thermal continuous radiation in just about 10 minutes, okay? So there's that. And now I'm going to bring up what, unfortunately, I usually do as a experiment. Okay, so let me new share. Okay, so what this is connected to a spectroscope. It's not connected now because I'm not in the classroom, but if it was here, you could see the spectra. So what I'm going to do is open an image I took earlier. And what this is the photograph on the left I took, and this was actually from a classroom demonstration I did last year. And we have a tube here, and the tube is glowing with helium gas, okay? And the spectroscope shows the lines that I've got with the cursor here of what I know is helium, but let's say I didn't know it was helium. And so over here is actually just a recording of that, of this, and it shows these lines here, which are the bright lines that are coming. So what we've got in the spectroscope is I've got the glowing glass of light. I've got a camera that has basically a prism in front of it, and that prism breaks the light out into different frequencies. And so when the prism breaks the light out in different frequencies, we see these series of lines, and those series of lines are recorded here. What's interesting is if I look at the lines that, say, hydrogen would produce, they don't match up. If I look at the lines that, say, krypton would produce, they most definitely don't match up. But if I look at the lines that helium would produce, they match up exactly. So by taking a photograph of the gas with a prism, seeing the lines that are generated, I can tell you right now that that was helium. So we could open up another image I took, and this time it's of, no, I'm telling you it's hydrogen, but let's say I didn't know that. And again, we see a series of lines, and those lines are represented by the red line here. And we can see here, I still have the lines that have been calculated by scientists, the lines for helium, and they don't match up. But the lines for hydrogen match up exactly. So basically what we have is these emission absorption spectra are barcodes for elements. So we can look at the spectra of any astrophysical body, and I can tell you what it's made of by looking at these lines, the emission or absorption lines. Does each element have its own unique absorption spectra? Absolutely, yes. You can tell every element has an exactly unique absorption spectra. Calculating absorption spectra is a big deal, but they have been calculated by other people. You can just look them up. Okay. Something I should mention is that helium. Have you ever wondered why helium, helos is another word for sun, why it's called helos? It's called helos because as they made these discoveries in the 19th century that we could use these barcodes, these lines, to identify elements, they obviously pointed towards the sun. And they says, oh, I can identify hydrogen, and I can identify carbon, I can identify nitrogen. And they says, but there's a bunch of lines that I can't identify. I wonder what those lines are. And so someone says, well, those lines must be an element we are unaware of. And we're going to call that element helium after the sun. And they discovered helium first on the sun 20 years before they discovered it on the Earth. It was one of the most amazing discoveries in science, especially in the 19th century. If you looked at a star with a prism, is it usually the same element, or does it change depending on the star? Jackson, it changes depending on the star, and we'll be getting into that in the second part of this course. So anyway, it's just amazing that we can tell you exactly what the universe is made of, specifically because of these absorption and emission lines, and because the locations of those lines depend exactly on the elements, and every line is unique for a unique element, okay? Let's kill that. Share. And let's go back to the presentation. Okay. So here we got a little quiz. So here we've got 4 graphics. I'm going to bring up the quiz, but you might want to look at, and unfortunately the quiz is going to hide the image, okay? So in the next minute, you might just want to like do a rough sketch of it. There's 4 quizzes here, and again, remember these polls are not graded, but after each poll, I'll clear it so you can look at the screen again, okay? So the questions I'm going to ask you is, which of these are absorption, which of these are emission, and what are their colors? And remember, the rainbow goes from Roy G. Biv, red, orange, yellow, green, Roy G, blue, indigo, violet, okay? And Roy G. Biv is low energy, the red, to high energy, the blue. Green is intermediate, okay? So here are the quizzes: absorption, violet or green, emission, blue and orange, okay? So the question is, which is which? So which of these, A, B, C, or D, is violet? Which of those, A, B, C, or D, is absorption of green? And remember the colors: blue is high energy, red is low energy, other things are in between. And then which of these is emission? Blue and orange. Okay, you all got that? Looking at this closely? Okay. And let me bring up the quiz. Alex, I love your background. Let's see. Let's do polling. So, which of these, A, B, C, and D, is absorption and would produce a violet light, not violent? Okay, 5, 4, 3, 2, 1, 0, -1, square root of -2, done. Okay, so most of you got correct. We know that it's absorption because absorption is where it absorbs energy, which means it has to go to a higher level. So we know it's either A or C, okay? Violet is much more energetic than green. Remember, violet is on the blue side. And so that means it has to be C, okay? And there it is. So let's stop that one, and then let's bring up the next question. And here is which is the absorption of green. And now that you know which one was violet absorption, the green should be really easy. 5, 4, 3, 2, 1, 0, -1. And you all got that, well, almost all you got that correct. It is you're absorbing, so you have to gain energy, so it has to be A or C, where the energy goes up. And green is much lower energy than violet, and so it has to be A versus C. Said, and then we got 2 more, of course. Emission of blue. Five, 4, 3, 2, 1, 0. And you got most of this correct. And let's do the last one for completeness. You should have no trouble with this one. And what's left? And that's correct. Okay. Okay, so now you got electron absorption and emission. We're going to be using that through the whole course. Okay. Now, here is the actual spectra of the sun. The actual spectra of the sun has a bunch of lines. In fact, I'm going to show you an image in just a second that has even more lines, but it also has this background shape to it. And the curiosity is, why does it have this background shape? Okay. It has this background shape because of what's called blackbody or thermal or continuous radiation. And there is the theoretical shape of that blackbody radiation. And by the way, if you take the spectra of the sun and stretch it out over just the visible spectrum, this is what it looks like. I mean, there's dozens of elements that are identifiable in the sun's atmosphere through these dark lines, okay? But the question here isn't that. The question is, what is the, what is going on with that overall shape, okay? And that's when we talk about blackbody radiation. But before we get there, I forgot to show you one other simulation, and let's show that right now. Okay, let's kill this. Kill XCD, go here. Okay, so this is where I've got a laser. I've got a light source here, and there's a screen there. And here it's a white light source. White, for the purpose of this course, is where you've got light of all the different frequencies. So when you see white light, it's got all different frequencies mixed up. There's no one frequency. If we put in a prism, or in this case, a diffraction grating, we've spread that white light into its rainbow colors: blue, cyan, green, yellow, red. Okay, there it is, rainbow colors. Now, instead of a white light source, which we'll talk about in a minute, we have an electron excited gas. And so this is where the electrons have been excited in the gas, and they will drop down and produce an emission spectra. And there's the emission spectra. And there's an emission spectra of a different type of gas. And again, if you look at the energies of those lines, you can tell exactly what gas it is. Okay, let's go back to the white light source. And here we have intervening gas that absorbs photons and produces those dark lines. So that's the difference between emission and absorption. Emission is where you've got hot gas where the electrons are excited. In absorption, you have some light source that's on the outside that goes through a cold gas cloud, and those photons are absorbed, okay? Got it? White light, the spectra of the white light, electron excited gas, there's the first gas, there's the second gas. Go back to the white source, and here we have an intervening cold gas that picks up those photons. So it's not directly symmetrical. I mean, that the frequencies of the absorption and emission lines are exactly the same, but the way they're produced are slightly different. Okay, so let's go back to our presentation. Okay, so we've talked about emission and absorption. We've talked about atoms. Now let's go to talk about black body thermal continuous radiation. And through this entire course and through all of science, we use a slightly unfamiliar way of talking about frequencies. Why does fire usually appear red instead of blue? We will be talking about that in about 4 minutes. We're all familiar with 32 degrees Fahrenheit and 212 degrees Fahrenheit. You're also always familiar with the fact that everybody else in the world, except for us and the Brits, literally everybody, actually I think the Brits are Celsius, everybody else in the world uses the Celsius system. That starts at 0 degrees C at water freezing and 100 degrees C at boiling water. We don't use either one of those in this course, and science doesn't use either one of those either. What science uses is what's known as Kelvin. Kelvin is basically the Celsius temperature scale, but offset by 273 degrees. And the reason we use the Celsius scale is that temperature is just a measure of the motion of the underlying particles. You're just measuring how fast the atoms are zooming around. So boiling water, the atoms are moving around really quickly. Freezing water, the atoms are moving very slowly. Well, if we're measuring the motion of these particles, there must be a point at where the motion stops, and that's called absolute zero. And so on the Celsius scale, absolute zero is minus 273 degrees. Scientists thought that was crazy. We should have a temperature scale that starts at 0 where all motion ceases. And that's the Kelvin scale. And that's why it's offset by this 273 degrees. Okay. So Kelvin is basically Celsius plus 273 degrees. So we'll be using Kelvin from now on, but just note that the different, it's when we're talking about millions of degrees, Kelvin and Celsius are basically the same. You also hear they use centigrade for Celsius. They're synonyms. And it's unfortunate in science and especially in astronomy, there's a lot of synonyms that mean exactly the same, and it's confusing. Why haven't we changed to Celsius like everyone else? Yeah, that's a really good question. Why haven't we changed to kilometers like every other country on the planet? Good question. I wish I had an answer for you. We actually tried to do it back in the 70s and it failed dismally. Okay. The reason why we're talking about that is that background shape you saw for the sun is known as a blackbody spectrum. What this means is that everything in the universe, if you take something and you heat it up, it will produce a range of electromagnetic light. And that range will produce this shape. In other words, it will produce a lot of this energy and less of that energy and that energy. This shape of light that anything that's been heated up produces is called a blackbody spectrum or a thermal spectrum or a continuous spectrum. One of those three, they're all synonyms, okay? And if we had another course in thermodynamics, I could prove to you how that shape comes about. For the purposes of this course, this is what you need to remember. This shape of this curve is unique for a temperature, okay? So if I take you and stick you in an oven at 7,000 degrees and I measure the light that emits from you, you will produce a spectra that looks like that. If I take your friend and throw your friend into the oven and heat your friend up to 7,000 degrees, they will produce exactly the same spectra, okay? So this spectra is unique for a particular temperature. And remember, the absorption and emission were unique for a particular element. Here we have the shape of the light coming off of an object that's unique for a particular temperature, irregardless of what it's made of. So it's kind of orthogonal to the absorption and emission. And the peak of this varies depending on the temperature, and the height of it varies depending on temperature. So as things get hotter, the peak goes to higher energy in the visible light, that'd be towards the blue, and it becomes much more of that light. So notice here, this is 7,000 degrees, and the peak is in the blue. Here at 6,000 degrees, the peak is in the green, but actually we would see this as white. And here at 5,000 degrees, notice it's much reduced, and the peak is actually in the red, okay? And again, this is true for all hot objects. Every object will follow this. So we're telling me we can make someone glow in the green. No, we cannot make someone glow in the green. And the reason why is when the frequency peaks in the green, we also have a lot of red and a lot of blue. And our eyes only have red, green, blue sensors. And so our eyes see, and actually our green sensor is less sensitive than the other two. And so what we would see is about equal amounts of red, green, and blue, and we would see white. So in fact, as you heat things up, they go from red to white to blue, okay? So there is red hot, white hot, and blue hot. There's no such thing as green hot. If you see a green flame, it's not being caused by thermal emission. It's being caused by absorption and emission. It's being caused by something other than black body radiation, okay? We call it we call it non-thermal radiation. Okay. So there's a glowing light. And so here's the thing. Every object in the universe, every thick object in the universe is glowing with this black body radiation depending on its temperature. Now here I gave you the examples of 5,000, 6,000, and 7,000 degrees. But you and me, we're glowing at 300 degrees. And so we have the black body radiation, but it doesn't peak in the visible light. It peaks in the infrared, okay? And so let me show you a computer simulation, and then I'm going to show you a thermal camera simulation. Well, it's not a simulation, it's real. I've got it with me. So let's go to, kill that. Okay, so here is black body at different temperatures. So there's 6,000 degrees. It's peaking in the blue. If we go to higher temperatures, let's start at 6,000. And so there's the peak. If we go to higher temperature, notice that it peaks at a higher thing, and notice that it's much hotter than this. If I go to a lower temperature, notice the peak is like that, okay? So the curve goes from very low energy with the peak in the red to very high energy with the peak in the blue and even higher energy, okay? Let's go to another simulation of the same concept. And I like this simulation because here it shows you what color it would appear. So, and here I'm going to control the temperature of the object. So we go down to a very low temperature, so low we can barely see it. In fact, we have to blow up the scale a little bit to see it, and there it is, okay? And it looks red, okay? And it looks red because it's only hitting the red sensor in our eyes. Now we increased a little bit, and now we get a little bit of red and a little bit of green, and our eye interprets that as an orange, okay? Now as we go even hotter, it's going to look even oranger. We have to reduce the scale because it keeps on popping up. And notice how rapidly the scale increases. And notice as we get even hotter, it's beginning to look like yellowish. And then when we get up to the sun, it looks white. It looks white. Even though a peak is in green, we've got so much blue and so much red that it looks white. And then if we continue on, it looks blue. So red, yellow, white, blue. And this is why it's weird because the And it peaks outside the visible light spectrum if the temperature is too high. That's exactly right. How would our vision change if we had orange, yellow, and purple cones instead of red, green, and blue cones? A good question, and the answer to that is in a book called Number by Colors, written by me. I talk about the human color vision, and the answer is mantis shrimp. We have 3 sensors in our eye. Mantis shrimp have 10. Mantis shrimp can have color experiences that are literally inconceivable to us. Okay, but that's a whole other course. Okay, so that's true for all objects in the universe. So now, is my camera still working? So I'm going to bring up my cell phone. Make sure there's nothing bad on it. Okay. And there we go. Here's my cell phone. Okay. And it's A+ for those of you that care. And on the cell phone, at the bottom here, I've got this, what's called a thermal camera. And what this is, it's a camera, but it doesn't detect visible light. It detects infrared light. And now I'm going to show you the screen. Okay. And that's me. You can see that my face is glowing red because I am glowing not in visible light, but in infrared. And if I turned all the lights off in this room, so this light is completely dark, you would still see this exact same image. Okay, there's the rest of that, and there's my face. Okay, so most of you are visible to me because light is reflected off of your surface. That's not what's happening here. Here, the light is being generated by the surface. So an infrared sensor is completely different than your visible light sensor. The visible light is looking at light that the sun generates light, it comes down, it bounces off you, and it's reflected. Here, the light is actually being generated by you, okay? So that proves to you that all objects generate electromagnetic radiation, but only objects that are in the 5 to 9,000 degree range we can see as visible light. If it's if the temperature is too low, we could only see it in infrared or other bands. If the temperature is too high, we can only see it in X-rays or gamma rays. Okay. So let's go back to our presentation. So that's blackbody radiation. And here are the equations for that. The equation for the maximum wavelength is 1 over the temperature. So as the temperature goes up, the wavelength goes down, the energy goes up. And there's gamma max. You are responsible for this equation. Again, not to calculate it, but know that the peak of the wavelength varies as 1 over the temperature. The total energy, which is the area under that curve, is proportional to the temperature to the 4th power. And that's why, as you saw with those graphics, the area grew just enormously, okay? Will the equation be provided on the exam? No, they will not, okay? They're not on the exam because you're not going to be asked to calculate anything. You will be asked a question like, if Rigel is at 10,000 degrees and Betelgeuse is at 5,000 degrees, and they're the same size, the same radius, how much more energy does Rigel produce? And the answer is, it would be 2 to the 4th power, okay? So that's the sort of equation, that's the sort of calculations you will have to do for the exam, you do have to do for the homework, and you will have to do for this course. Those proportional exams, you will not be given the exams, but here are all the equations, but here are all the equations that you need. The the wavelength max is 1 over the temperature. The total energy is temperature to the 4th. This third equation, unfortunately, I don't have time to go over, but we'll go over that later. Okay. So that is continuous black body or thermal spectrum. That would be, well, we don't have these anymore, but the old-fashioned light bulbs that actually glowed. So the old-fashioned light bulbs, every now and then you might see them. not the fluorescent, not the LED light bulbs, but the really old-fashioned light bulbs, that filament actually glows at 4 to 5,000 degrees and produces the light. It produces a thermal spectrum, okay? Absorption spectrum, where you have a thermal spectrum here where that light is absorbed by intervening gas clouds. And then we have emission spectra where the atoms are excited and then will produce light, okay? Absorption spectra, emission spectra, and continuous spectra, okay? Doppler effect, I'm going to have to go over this quickly. Doppler effect, we're very familiar with Doppler effect in our day-to-day lives because Doppler effect affects the way we hear sound. So what you're going to hear next is a bicycle approaching us. So the frequency was shifted up as it came towards us and shifted down as it went away from us. There's another one. That shift in frequencies depends on the motion. Sound travels at about 760 miles an hour, and the sound that approaches us has a higher frequency, a shorter wavelength, and the sound that goes away from us has a lower frequency, longer wavelength. And that's just because the mechanical bunching up of the peaks of the wavelengths has approached us and spreading out as it reduces us. Next, you're going to hear an American siren. And here's the problem with that. The American siren produces this sweep up and down in frequency. And as the siren passed us, you really couldn't tell whether it was moving away towards us because your ear can't pick out any shift because the frequency is always moving up and down. Well, the Europeans did us one better. Here's a European siren. And notice as it passed, it went up and down. Now, normally I would stop here, but I have to finish Doppler, so I'd propose I'm just going to continue on to 11:30, and then we'll just have to break. Hold your questions for the next lecture. Sorry about that. So Doppler effect, higher pitch moving towards us, lower pitch if you're moving away from us. The same thing happens with light. When you move an object towards you, the frequencies are bunched up. So it's a higher frequency, shorter wavelength, higher energy. And we call that blue shifted, because remember, blue is higher energy. If it's moving away from us, then the frequency, the wavelength is longer, the frequency is less, the energy is less, and we call it red shifted, because remember, red is lower energy, okay? So the Doppler effects works both for sound and for light. And because of that Doppler shift, we can detect velocities of astrophysical objects. We can detect whether they're moving towards us or away from us. And remember, the light for most objects has these series of absorption lines, and we know exactly what those frequencies of those lines are. If we see those lines shift, we know the object is either moving towards us or away from us, okay? So here's the at rest. Here's its red shifted, the lines are moved that way. Blue shifted, the lines are shifted that way. Red shifted means it's moving away from us. Blue shifted means it's moving towards us, okay? But we can only measure the radial velocity, not the actual velocity, because there's a transverse velocity that we can't measure, okay? And here is the equation. It's the change in the wavelength over the wavelength is equal to the velocity over the speed of light, okay? So here we've got an example, and this should be my last slide. Here we have an example where we have, this is a fixed spectrum. Here's the sun, which is essentially fixed. And here's a Spain spectrum of a star we're looking at, which is shifted by 0.155 wavelengths, okay? So how quickly is that star receding from us? Well, it's the difference in those wavelengths over the wavelength is equal to velocity over c. This looks like a complicated equation, but it's not. Here, the difference in wavelengths is 0.15, as you can see there. So the radial velocity is that 0.15 over 882.4, which is the baseline wavelength. And that's equal to VR over c. So I just move that c over, multiply it by 300,000 kilometers a second. And this simple equation tells us that with that 0.15 nanometer shift in the wavelength, it's moving at 50 kilometers per second. Okay. And that's the equation there. And I'm done. We've got 10 minutes for questions. Thank you so much. Okay. Go ahead and open your mic if you want. And remember, any questions you ask, you have to be on chat at least 5 times during the semester to get full credit for class participation. Any questions?
I have a question, sir.
Yes, go ahead.
So on the exam, when we have to do stuff with the color spectrum, I'm partially colorblind, so will everything on the exam like have a label to it, sort of?
Yeah, there's no color on the exam for that
Okay.
exact reason.
Okay.
So my advisor was colorblind, and actually, you're probably red-green colorblind. That's true for 90% of the males that are colorblind. And you actually are not colorblind. You have reduced color discrimination.
Mm-hmm.
And I knew a woman in her 20s who didn't know she was colorblind. So it's interesting. The thing is, well, this will take us far afield, but you can actually perceive a green that normal people cannot perceive. And you don't know it, and you have no way to describe it. But most of us, we cannot, because there's overlap in the sensitivities of our red, green, blue sensors, especially in the red, green. You can never ping our green sensor in a normal person's eyes and not ping the red sensor. So there's no such thing as a pure green, except for you. You can see a pure green, but you can't describe it. You know, so it's just kind of interesting. Is it true? Let's see. Is there a material that can absorb or reflect light in one way, non-reciprocal? There's something that just came out that can absorb all light. I forget the name of it, but it became a point of multiple lawsuits and millions of dollars. That it's very, very difficult to absorb all light, and that's about as far as I know. Is it true that girls have one more cone than guys do? So Colson, no, it's not true, but yes, it is true, and let me explain. All human beings on this planet Earth, with, as far as we know, only one exception, have 3 cones, and we can see with 3 different colors. And that's true for 7 billion people on the planet. The one exception was a woman in Great Britain who was taking part in a research project who has 4. Okay. And she can perceive those 4 different colors. So she actually has 4 useful color cones. And we don't, certainly you could imagine some genetic tweak where they would create a 4th cone, but she actually has the brain is wired to make use of that. And that just kind of blows my mind. But that, as far as we know, and what's it like to have 4 cones? She has no way of describing that to us. I mean, and she didn't know. It literally inconceivable. We cannot conceive of color, just like we cannot conceive of 4 dimensions. I can talk about 4 dimensions. I can write down equations for 4 dimensions. I can make analogies for 4 dimensions, but I can't actually tell you what it feels like to be a 4-dimensional object, being in 4 spatial dimensions. And she can't tell us what 4-dimensional color is like. Is there any way for colorblind to see what non-colorblind people can see, or vice versa? To a very limited extent, yes. With special glasses, what those glasses do is it enhances colors, it shifts the colors. And again, very few people are purely colorblind. What they do is they have reduced color sensitivity in the red-green range. And the red-green range is where most of the action happens. And so if you separate the red-green range and increase that range, you can give the greater color discrimination, and you can emulate normal color vision with someone that's colorblind. But it's imperfect. What are protons, electrons, and neutrons made up of? Good question, Nicole. Protons and neutrons are made up of quarks, and we'll be talking about that when we talk about the Big Bang. Electrons, as far as we know, are not made up of anything. They're primordial. They are electrons. Why are electrons? That's a question we just don't know how to answer. That's the way the universe has worked. Vanta Black, yes, Sam, that's correct. Thank you for finding that. How do enchroma glasses work? Brody, I'm not familiar with that term, but I think if what I described is it, then that's what they are. What colors make up the spectrum we cannot see? Colors, by definition, are visible colors. The electromagnetic spectrum consists of energies that span, 50 orders of magnitude, and we can only detect light that spans from 400 to 700, and a micro scale. And our term of color explicitly means visible color, the colors that our eyes can perceive. If it's outside that, color doesn't really apply. That term doesn't apply. So what we apply is energy or frequency or wavelength. I think there's a video about the glasses. Yeah, I should look that up. Why is red-green color blindness more common? Good question. I don't know. I do know that if you look at the physiology of the blue sensor versus the red-green sensor, the red and green sensors are almost identical. There's very little difference between the two. So clearly what happened, and this is true in some animals such as dogs, is we evolved from a two-color sensor being. So we had a blue cone and a red-green cone, as many mammals do. And then at some point there was a genetic defect, genetic change, where some of those cones turned into red and some of them turned into green because they're very chemically similar. And the reason why this was advantageous is that there's a lot going on in the wild between the red and the green. Green especially, everything's green. Anything that's even slightly off green is something we need to worry about. And for those people that are red-green colorblind and you don't have much perception of the red-green range, that the red-striped lion is not going to be as visible as it is to you and me. There's a YouTube there. Is anything smaller than a quark? I don't know. There are postulates that quarks are not fundamental, that they're made up of something else, but that's not that's outside my realm. So Art, I'll look at that video once we get offline. Other questions? Okay, if no more questions, we will.
Love you, Brand.
Thanks so much. I appreciate that. Oh, wow. So Art, thank you. Art sent a video of the color blindness thing. Let's bring that up. And since we're going to go past 11:30 with this video, feel free to just sign off.
A while back, there were a whole bunch of videos that went viral. Someone who is colorblind puts on special glasses and suddenly they can see the world in all its colorful glory. Some people freak out, some people cry, some people can't stop staring at colors they say they've never seen. When we first heard about this, we were like, we need to make a video about that immediately. And then we spent years basically trying to get to the bottom of it. And this is the culmination of that. Thank you to our writing staff. So, obviously, these glasses don't just turn on a bunch of new colors for colorblind people. And when people put the glasses on, they aren't suddenly seeing the world the way that people with normal color vision do. The glasses just filter light in a way that makes it easier for people with certain types of colorblindness to tell the difference between colors. If someone's colorblind, that means that something's up with the cones in their eyes, the photoreceptors that detect color. There are 3 types of cones for seeing short, medium, and long wavelengths, which roughly correspond to blue, blue, green, and red. There are lots of different types of color blindness, and in almost all of them, people can see at least some colors. The exception is monochromacy, where people don't have any cones at all and they see the world in black, white, and gray. But that is incredibly rare. Only about 1 in 30,000 people have it. There's also dichromacy, where one type of cone is missing, where someone is missing all of their green cones, for example, they see at the.
Okay, that's it. We're out of time, so I will see you all on Thursday. Thanks so much. It's been fun.